Good morning to all of you. I'm Alberto Campagnolo from University of Padua. I will now present the work entitled Automated Fatigue Strength Assessment of Arc-welded Structures According to the Peak Stress Method. The co-authors are Giovanni Meneghetti and Alberto Visentin. This work deals with the automation of the fatigue strength assessment of welded structures in a modern everyday design practice. In this perspective, an interactive application has been developed within ANSYS finite element software in order to automate the post-processing of a structural finite element analysis of welded joints according to the peak stress method, as in the example reported in the figure, where a key joint is analyzed and the estimated fatigue life is plotted along the weld toe lines, predicting fatigue failure where life is minimum in agreement with the experiments. The peak stress method is a rapid technique to rapidly estimate the notch stress intensity factors from the linear elastic peak stresses. More in detail, considering the sharp V-notch at the weld toe side, the opening stress is used for mode 1, the in-plane shear stress is used for mode 2, and the out-of-plane shear stress is used for mode 3. All stresses are calculated at the notch tip by using coarse and free meshes having element size equal to D. The main advantages of the peak stress method is that coarse and free meshes can be employed and only the linear elastic peak stresses suffice to be considered. On the other hand, parameters KFE stars depend on the element type and formulation, on the finite element mesh pattern, and on the procedure to extrapolate stresses at nodes. Therefore, a calibration of these parameters is needed. Several element types have been previously calibrated, such as 4-node plane, 8-node brick, 4-node as well as 10-node tetra elements, provided that minimum mesh density ratios A over D are respected, where A is the characteristic size of the joint. The strain energy density averages over a structural volume of radius R0 and surrounding the crack initiation point, that is the weld toe or the weld root side, is assumed as a damage parameter for welded joints undergoing fatigue loading. The structural volume size R0 is a material property which is equal to 0.28 mm for steel joints or 0.12 mm for aluminum joints. The average set can be expressed in closed form as a function of the notch stress intensity factors, which in turn can be rapidly estimated by using the peak stress method, so that the closed form expression of the average set can be rewritten as a function of the peak stresses. Then, by considering an equivalent uniaxial stress state, an equivalent peak stress can be defined according to this expression and can be adopted in the same way as the average set to assess the fatigue strength of welded joints. The equivalent peak stress has been adopted to reanalyze about 2,000 experimental fatigue data relevant to aluminum or steel welded joints. As an example, dealing with steel joints, several welded details have been considered. The main plate or tube thickness was between 2 and 100 mm, while the base material was a structural steel having yield stress between 235 and 770 MPa. The experimental results were generated by fatigue testing as welded and stress-relieved joints under pure axial, pure bending, pure torsion, and combined bending torsion or axial torsion in phase or out of phase fatigue loadings. Both weld root and weld toe fatigue failures were included in the database. In order to select the proper peak stress method-based fatigue design curve, instead of using a nominal biaxiality ratio, a local biaxiality ratio has been recently introduced and defined as the ratio between the energy contributions tied to the shear modes of loading, that is mode 2 and 3, and the energy contributions tied to the opening mode, that is mode 1. It has been shown that fatigue results having lambda equal to 0 fall inside a design scatterband having category equal to 156 MPa and slope equal to 3. while fatigue results having lambda greater than 0 fall inside a design scatter band having category equal to 257 megapascal and slope equal to 5. Once calculated the equivalent peak stress for a welded detail, entering the proper fatigue design curve allows to estimate the fatigue life. It seems easy to apply the peak stress method. Sure it is, but the method presents delicate requirements and application steps. This video shows all the steps required to manually apply the peak stress method to a solved finite element analysis of a tube-to-fly joint under combined axial and torsion loading and meshed with 10-node tetra elements. In post-processing, the analyst must first check some geometrical parameters, the characteristic size A of the joint, which is in this case the weld line length, and the adopted element size D. In this way, the mesh density ratio A over D can be calculated and compared with the requirements of the method as a function of the loading mode, the opening angle, and the element type. In this case, only mode 1 and mode 3 are present, and it can be observed that all requirements are satisfied. After that, the analyst selects the model's line and all the nodes attached to it. 3 coordinate nodes are required for current evaluation with tetra elements. The middle sign nodes of tetra elements have 0 stress values and must be discarded, keeping only coordinate nodes. After that, a local coordinate system needs to be manually defined on each node in order to calculate the proper opening normal peak stress relevant to mode 1 and the out-of-plane shear peak stress relevant to mode 3, all calculated with reference to the notch bisector line. The peak stress method based on tetra elements requires to calculate a moving average peak stress on 3 adjacent corner nodes of the line to smooth the variability of the stress calculated by using tetra elements. Now, the equivalent peak stress can be calculated by introducing some correction factor. CW terms equal 1 when considering as welded joints, while FW includes material properties, shape factors, and peak stress method calibration constants. Therefore, the equivalent peak stress can be now calculated, and also the local biaxiality ratio can be defined, and the minimum plate or tube thickness can be checked, and then the proper fatigue design curve can be selected. Once known the equivalent peak stress, it can be compared with the fatigue design curve, and the estimated fatigue life results to be equal to 240,000 cycles. The aim of this work is to develop an application able to automate all these phases. To do so, 3 main programming languages supported by ANSYS have been used. UIDL is a graphical programming language allowing to develop graphical features within ANSYS interface. 2 control files allow to extend ANSYS standard main menu, creating a new interface completely dedicated to ANSYS PSM app. APDL is instead a parametric language allowing to program the different functions of ANSYS finite element code. 15 APDL macros were developed in order to automate the peak stress methods workflow and develop dedicated post-processing functions. Finally, DCL-TK is an accessory graphical language allowing to develop and import custom widget tools and contents within ANSYS interface. But making the application of a peak stress method automatic doesn't mean only compiling a series of predefined commands. That is what led to the development of the automatic V-notch identification routine. A V-notch is defined as a structural, sharp, V-shaped geometrical feature characterized by an opening angle lower than 180 degrees. V-notch hotspot in 3D finite element models are the model's line. The routine selects each line and the nodes attached to it, then generates on each nodal position a circular support area. The areas are intersected with the model's volume, and the remaining circular sectors can be used to locally evaluate the V-notch opening angle. When a V-notch and its opening angle is identified, the local coordinate systems can be automatically defined and orientated. Then peak stress values can be calculated and fatigue life can be estimated according to the peak stress method. Another development deals with the life control plot function, namely a function allowing the code to generate color plot reporting estimated life depth distribution along the model's lines. A first solution aimed at substituting life results to existing solutions in order to use a predefined plot. This solution was actually discarded because of high computational time required and low plot quality. In order to increase plot quality, a second solution was introduced by using a nodal path plot. Also, this second solution required high computational time. The first solution consisted instead in creating a thermal contour plot, making use of link 33 elements. Thermal elements are automatically deposed between consecutive structural nodes on the identified V-notch lines. Respective life results are applied to the nodes as temperature boundary condition, and a thermal analysis is finally performed. Such analysis will indeed be instantaneous, having link elements only 1 degree of freedom. Once analysis is solved, link elements, temperature table, and model's line can be plotted together. ANSYS PSM app presents a main setup menu through which the user can consult and define essential parameters and settings such as element type and referred material. Geometrical parameters include the characteristic size A and element size D, while other settings include loading condition and fatigue curves. Then an analysis setup menu allows the user to account of the estimated analysis time and to select the analysis method, automatic to apply peak stress method to all lines of the model, or manual to select only the desired lines. A post-processing function cluster is included for life data visualization and handling. Making part of this section are query life results function, allowing the user to visualize numerical life results by manually clicking on the model's geometry, and life contour plot function generating colored life distribution plots. The analysis log finally is intended to collect and provide all information generated by the code during its workflow. Let's now see the automatic application of ANSYS peak stress method to the previous tube-to-flange joint. The analyst has to input the main geometrical parameter. The lateral support menu includes some predefined examples which can support the analyst to select the proper parameter A. Then the survival probability must be selected for the fatigue design curve, and after that the mesh compatibility can be checked. It can be observed that all requirements of the peak stress method are respected for both mode 1 and mode 3 loading. The analyst can account for the expected time for solution and can select an automatic analysis. Line by line, the model is processed, the V-notch spots are identified, and the peak stress method is applied to them, estimating life. The total elaboration of this model lasts 40 seconds. When the analysis is completed, the analyst can check the estimated fatigue life, and it can use the query life results, obtaining an estimated fatigue life of 240,000 cycles as expected. Another case study is relevant to a large-scale steel welded structure which represents a detail of a slice gate having overall size on the order of tens of meters, while the considered detail has size on the order of meters. The detail is characterized by many different welded geometries, including T and cruciform joints, both fillet and full penetration welded. The plate's thickness ranges between 10 and 58 millimeters. The model was simulated within ANSYS by using 10-node tetra elements and by adopting a mesh with element size equal to 5 millimeters. The 3D FE model has been solved by taking advantage of ANSYS HPC by using 10 cores, the global number of degrees of freedom being equal to 10 millions. An ANSYS peak stress method full automatic analysis was finally launched on the model reported here. As shown in the previous example, the analyst takes account of different information dealing with element type and material properties. After that, the main geometrical parameters related to the model must be input. Then, the desired survival probability for fatigue curve must be selected, and the mesh quality must be consulted. After that, a full automatic analysis can be launched on the entire model. The calculation takes about 26 minutes for the entire model to be completed. At the end of the process, the following life distribution plot has been generated. It is normalized with respect to 10 to the power of 15 cycles, and the plot aims at locating the maximum and minimum fatigue life hotspots. In conclusion, developing such interactive application allows to extend local approaches to modern everyday design practice. A remarkable time reduction can be noticed from the comparison reported in the table for two case studies, the first one with size on the order of tens of millimeters, and the second one instead with a size on the order of meters. The application is moreover simple to use within a reach of either expert and novice analyst. A single setup menu needs to be completed before running an automated fatigue analysis on a generic weather structures. Among future developments is the possibility to extend ANSYS pictures method to other finite element softwares and also other environments of the same ANSYS suite, for example, ANSYS Workbench via ACT. This app, however, builds a starting point for the development and optimization of more new applications, eventually extending also other local approaches to everyday design practice. With this, I have concluded. Thank you for your attention.